All right, so thank you very much for the introduction. I'm Robert, talking about Deus Machina, which allows a smartphone to provide contextual functionality by tapping it to a device. So traditionally, we interacted with devices by physically walking up to them and interacting with buttons, switches, and knobs. And this style of interaction is, pretty traditional, it's familiar, it's intuitive, and it's intentional. But lately, though, we've got the Internet of Things. The trend has been moving towards centralizing control on your mobile device, seemingly with a special app for every single one of your devices, every single gadget. So, you've got an app for your smart thermostat, you've got an app for your Wi-Fi router, your internet-enabled printer, your mesh networked light bulb, and so on. Many of these IoT devices lack any sort of physical interface at all. They rely exclusively on remote access. See, this Chromecast audio I've got up here is a great example. There's no physical buttons at all on it. You're supposed to control it entirely with a phone app. And although these apps offer an interface that's often a lot richer than traditional physical interfaces, but there's something missing now. You can't just walk up and use these devices like you could before. You've got to go on your phone, digging for an app, and then launch that and get it configured. So what we're showing is Deus Machina, a technique that allows phones to detect appliances on contact, and then summon appropriate interactive functionality. Our technique is based on electromagnetic sensing. Specifically, we sense the electromagnetic noise that's given off by electrical appliances. Notably, our technique doesn't require the appliances to be instrumented at all. We simply rely only on the noise that they already give off. So, following a grand tradition, I'm also going to attempt a live demo. So right here, I have a phone, which we've modified by adding an antenna inside, like you can see on screen. So there's a little copper foil antenna behind here, and to that we've attached basically a sensor board that incorporates an amplifier circuit and microcontroller, and I'll talk a bit more about the details later. We use the microcontroller's ADC to sample some baseband radio signals. Okay, so right here you can see this is actually a live view of my phone. So all the things I'm doing in here is just casting directly to my computer. And you can see here is the signal. This is sort of the background signal. So I wave it around. There's not really a whole lot of EM background because I've already sort of calibrated that out. But if I touch it to some object, so, whoa, what happened? So like this internet router that I've got sitting on the table, there's a bit of a signal there, right? And this sort of Wi-Fi printer over here, different signal. This light bulb, actually, has a very distinctive electromagnetic signature. Even my smartphone has a little bit of an electrical signature. So every device that I tap is going to have its own unique signature. Like this camera right here, the LCD puts out a lot of EM. So we can actually, what I can do here is sort of switch this to a classifier view and show you this classifying. So there's the printer. We've got like a light bulb over here. Even sort of trained it on my trackpad here. So all these devices can be detected on contact. And you notice basically that EM field doesn't extend very far. If I'm close to the object but not really touching it, it doesn't really trigger. So we can actually do some really interesting stuff with this. So for example, I've got this light bulb here. If I actually tap my phone to the light bulb, I get a light bulb control app. I turn that on. Okay. Well, I could turn it on. Demos, right? So I can turn on sort of like a light bulb control, or in theory. Or another example is if I've got a document pulled up on my phone, so to do contextual stuff, right? I can actually tap it to here and get like a little printer icon. If I tap that printer icon, I'm assuming the Wi-Fi is probably down. Thanks. So that I can get the printer icon, and that can allow me to actually print to that document, right? So I detect that, that's contextual. But the document, you can do other things with it. So if I tapped it to my computer, for example, a different icon shows up, and this little icon means send to device, send to the computer. So I can do things like, either print to the device when I'm near it, or I can send it to my computer. And notably, I can have a whole bunch of these different actions, but I don't have to have any space on my screen for that. That's all contextual, right? And I don't have to like explicitly walk into a bunch of menus just to do it. I can just say, okay, I just walk up to the device I want to use and go for it. Okay, so that's the demo. So now let me just sort of go briefly through related work. So a lot of previous systems, even commercial approaches, have sort of proposed tagging appliances so that they work with mobile phones. This is, for example, using QR codes, NFC tags, RFID, so on and so forth. But the important thing about this is it requires appliances to already be tagged and instrumented. And that's a significant barrier to adoption. Because if you say, okay, well, all of these devices have to be tagged already in order for you to use them, if an untagged device is actually kind of useless to you, you have to, there's no advantage for that. So closer to our work are systems that detect uninstrumented appliances. For example, proximity-aware controls on the left, they used basically a tightly calibrated room where all the objects are predefined, and so the location of the phone within that room determines sort of what interfaces would show up. Snap to It, presented at Chi last year, is a little bit closer yet, which uses a phone camera to detect uninstrumented appliances and present an interface. So sort of a similar idea, but with a very different sensing technique. For the technical approach of sensing electromagnetic signatures, a lot of past systems have actually tried to use that for different purposes. For example, EMI SPY used 100 kilohertz sampling rate, and that allowed them to detect different users touching different LCD panels. MSense, on which our technical approach is based, was a smartwatch-mounted EM sensor for sensing objects that users touched or interacted with, and that was used for activity recognition. Okay, so let's talk about the implementation then. Like I showed you earlier, our hardware consists of this copper antenna that we sort of inlay on the back of the phone. Now, in a practical device, this could actually just be replaced with the metal chassis, for example. A lot of phones are made out of magnesium, aluminum, or just plain metal, which could be used, which can transmit the electromagnetic signatures. Or it could be, or we could attach our sensor basically to a suitably large built-in antenna, like the NFC antennas that are often built into the backplane of some new devices. This antenna is connected to an amplifier circuit that's on a custom PCB, and that amplifies our passive EM signature that we're getting from the antenna, feeds it to the ADCs in a 84 megahertz ARM microcontroller. And now note, this is a $4 microcontroller. There's nothing special about it. It's really basically an off-the-shelf part. This microcontroller has two ADCs on it, and we actually feed the antenna signal to both of them. We overclock that ADC to about 2 megahertz each, and then we actually time them slightly offset in time so that they sample in alternate cycles. That gives us basically a 4 megahertz sampling rate. So in total, by Nyquist sampling, we can get up to 2 megahertz of clean signature. And that gives us a huge bandwidth to work with. That's how we can distinguish a lot of different devices. Our sampling rate is actually so high that we need to offload data copying to the DMA engine on the device. And once there, basically the chip periodically pulls that buffer off, the CPU on the chip, performs a fast Fourier transform, again, all on the microprocessor, to convert that into a frequency spectrum. And then we compress that by removing the phase information that's not useful for our classification. We then stabilize the EM signature using a maximum filter over time, and then send it as raw frames to the phone over a USB serial connection. And of course, in a real system, we'd use something like a built-in sensor hub that's connected directly to the phone CPU for these kinds of computations. To classify each incoming frame, we built a classification engine that runs directly on the phone itself, the phone's main CPU. Here's a list of the features that we derive from the raw data frame. We use basically an SVM classifier to actually classify these objects. It's a 1 versus 1 binary classifiers for every pair of objects, performs basically voting to determine which one is the most likely candidate. It takes about 45 milliseconds per frame for our 17-class classifier that I'll talk about a little later. We actually stabilize that classification by taking the mode, the most frequent classification over the past second of data, so that we don't flip classifications if some errant noise pops by. After we get the classification, we can then pop that up one layer to the Android intent framework. And so this is built on standard Android. The software itself, there's no kernel modifications to this time. We can basically broadcast an intent that carries with it the object class that was detected, and these can be received system-wide. So for example, we can launch a full-screen app. So if, say, you have a Linksys router, you download the Linksys app on your phone, and then it could register with the system, say, okay, every time I receive a router notification message, maybe pop up this app, or a router of this specific model. Broadcasts are system-wide. Apps can install basically their own broadcast receivers for custom functionality. But for the contextual charms, those little the printer icons that I showed you earlier, we actually provide a library called libcharm. And that provides the unified UI, the little popover icons, as well as an object recognition system, a registration system, rather, for objects to support these charms. So applications, what they do is they just register a verb that they support. So I'm capable of printing. I'm capable of sending files. I'm capable of transmitting media or casting media. And then appliances also register those verbs as well. Every time you touch an appliance, we take the intersection of the supported verbs, and we present icons appropriate to the actions. So this is a sort of an appliance agnostic approach where we don't really care what the exact appliance is as long as it supports the actions that we request. Okay, so that's the software stack. To validate our system, we carried out an evaluation of the system's accuracy. In preparation for the study, we selected 17 appliances and collected EM signatures for each one. In order for us to achieve some temporal stability, we collected this data over 2 separate days. In all, we collected 20,000 signatures, then trained a classifier that runs directly on our phone. And in this video, you can see our devices along with their characteristic EM signatures and our classifier detecting each one of these devices. I'll just run that through. You can see some of the signatures are smaller than others. Certainly some devices are better shielded, require lower power, etc. But they still all give off some sort of characteristic signature. All right. So what we did was we did a user study with 10 users, 30 minutes per study, and we used a pre-trained classifier to recognize objects as they moved around the space. 10 users tapped on our appliances spread out over 5 different areas. We collected the output of the pre-trained classifier and used that to determine accuracy. We did not do any post hoc classification at all. So this was all done on device, whether it was correct or not. Our results show that we can classify all 17 objects at an aggregate of 98.8% accuracy. 14 of our objects actually achieved perfect accuracy throughout our study. And we didn't find any temporal effects over the 3 separate days, nor any user-specific effects or effects from our different zones. And here, if you like confusion matrices, there they are. The legend for all of these different devices can be found in the paper. All right, so finally, I'd like to close off by showing you some more applications of our system. I showed you a couple in the live demo sort of briefly. So here's a bunch of different full-screen applications that we can launch. So here, for example, we can control a thermostat, and you get a much better thermostat experience than the little buttons on the front. Here, this is a projector application. Now, this one actually works for real. We reverse engineered the Crestron control protocol that the projector uses, so we can actually send control commands to it, change the the input source and other properties. Here's a door lock application. So this is a magnetic access controlled door lock. And what we can actually show is a history of all the people who've logged into it. This is a mock-up. And add people to the access list. For TV application, you can touch the TV and use it like a remote. Maybe you've forgotten your remote, but you've got your smartphone handy. And the Wi-Fi router application. So this is being able to touch it to the Wi-Fi router and actually control the settings. This is beats typing in like 192.168.1.1 into a web browser. So for a fridge, we can access different properties of the fridge. Yeah, query its status. And again, the sort of light bulb, this one actually works. So basically being able to change the color of the light. So it's like having a super light switch, right, with this kind of thing. All right, and then we also have a set of contextual charms. So if I touch the printer, I get a little charm that pops up. It actually prints to the device, right, and a little while later, basically the printed files come out. So this is another example with touch it on the monitor. I can get like a little send to file thing. So I can approve that file transfer. It comes up. This is all real, by the way. All these were filmed basically with an actual working implementation. There's no mocking in this full stack implementation here. The other thing we can do, so a computer supports both receiving files. It also supports clipboard pasting. So I can select a little bit of text, and actually I get a second contextual charm once I've selected some text. That's paste. And so what I can do now is I can just go onto my computer and just paste that text. Because this is a case where I register 2 verbs. And so this is a case where one verb actually applies to 2 different devices. So this is a cast verb. And so if I've got some document on screen, I cast it to a TV, cast the video, or I can cast some audio to this Chromecast audio. All right, and that's basically it. Thank you very much for listening.
Hi, Antonio Gomes, MIT CSL. Do you suspect that your sensing hardware will react differently to different users or to different phones? Did you evaluate that, or did you observe that by any chance?
So in we only sort of have one phone sensing platform, and so we didn't investigate the effects of different phones. We did investigate the different effects of different users, and we found that there was no user effect. So basically, across our 10 users, there's no discernible effect between the different users as far as like how they hold it or how they change the electromagnetic signature.
Thank you. Excellent work.
Yeah, excellent work. Yeah. And I want to. My question is that whether like the same model of the computer or other appliance have the similar signature across like different models.
Yep, that's a very, very good question. So one of the things that's very interesting is different models of the same device. So Apple laptops are a great example. The trackpads actually behave differently on different devices. That's a function of what's inside the computer, how the trackpads are actually manufactured, and a bunch of other things. So different models of the same manufacturer can often have different signatures. They don't have to. But the same model of the same machine often has very, very similar signature, and we can't distinguish that. There is, however, some research from Disney, for example. There's MID that suggests that we can, if you do a different sort of analysis, distinguish the same, this different devices with the same model but different serial numbers, basically. And there's also a possibility in the future of doing things like geolocation to distinguish different devices that are in different locations but similar models.
Okay. Yeah. My second little question is that it seems like you train like all the classification of all those devices at one time. So is it easy to like add another model in afterwards? Because
yeah. So it's certainly our actual vision for this is that you would have some sort of like so how we actually envision this being used in practice is having a library, a cloud library of different signatures, and you would download the ones corresponding to your devices that are in your home, right? There might be collisions in the cloud, but you download them to your device and add those together. Adding new devices to the classifier is not that challenging. Basically, you add another sort of one versus one classifier to the system, and it's done. Yeah.
Okay. Thanks.
Yep. Hi.
Hi, Margot Bruton from QUT in Brisbane. Look, I think it's very nice work, but my understanding of the IoT and a lot of these home automation apps is that people are using them at a distance in order to turn something on when they're not there. And when you're there, I think something like the Nest thermostat with a purpose interface would actually be much more satisfying than a phone app. So how do you take the loveliness that's in the technology that you've got and find a way to get the tangibility experiences, and have you sort of considered what to do there?
We've certainly seen, obviously, the Nest thermostat's a great example of one that they have built a great sort of physical UI into. And we do actually really appreciate that. Obviously, by all means, you're recommended to use the physical UI where it's possible. Problem is that a lot of IoT devices have sort of gotten to the point where they're like, well, we don't really need, we've got these phone apps, right? We don't need like a physical interface because they're expensive, it's hard to produce, it requires a lot more attention to detail. And so you have things like the Chromecast Audio, the Chromecast devices that are just headless. There's no interface on them. And so for those devices, what I'm doing is trying to provide an interface. And again, it's kind of interesting because if you've got a phone app and you're saying, okay, you can control these from your office, surely controlling them when you're next to the device should be easier than controlling them from across town, right? But right now, the case is that it's the same amount of difficulty. So I want to sort of alleviate that with Deus and Machina. Yeah.
Thank you.
Hello, I'm Roman Hursto from MIT CSL. I was curious whether the signature of devices such as laptops